Oh yeah, Hitching a Ride, a tale of a well-traveled Bukia. Well, not sure what the problem is here. Okay. So when I visit family down in the Puget Sound area of Washington State, in particular Mukilteo, which is across from Whidbey Island, which you can see in the distance there, we like to go walking on the beaches just for exercise and looking for things that we might be able to find there. And so Edgewater Beach in Mukilteo is the site of the ferry terminus from Mukilteo to Whidbey Island. You can see that in the background there. That's the old ferry terminal. There's a new one apparently. And as well, if you turn around 180 degrees and look the other way, you'll see the Mount Baker Terminal. And the Mount Baker Terminal is where Boeing brings in big pieces of its larger airplanes and that are manufactured overseas, loads them onto these rail cars that you can see here, and then takes them by about a 2-kilometer railway up to their production facility at Payne Field. And so it's a pretty complex area. But you can see here the beaches are riddled with a variety of different sediment types. So at the high levels of the beach, protected by the berm of logs and boulders that have been brought in, we have a lot of fine sand accumulating. And when you get down below that into the area of the tidal zone, you can see there are a lot coarser rocks and cobbles that are found there. So we have a lot of coarse sand here, dark colored, with lots of white, light colored shell debris, broken up fragments. And as well, there are areas of the beach where you get extensive cobbles. Now, most of these rocks, these cobbles, are of volcanic composition. They're derived either from the Cascades crystalline core, older volcanics, or from the younger Cascades volcanic arc that's active today. And so it's pretty mundane looking around at the rocks and cobbles because all you find are volcanic rocks, right? And therefore, when you go down to the beach, it's primarily for exercise and fun. Now, my family likes to go hunting for beach glass. And so these are fragments of bottles. And the one on the bottom here in green is a float. And these pieces have been broken up over the years and crash around in the surf and get rounded up. And, they form little treasures that some people like to collect. But one time I was down on the beach and we were looking for these beach glass fragments, and I looked down at my feet and I found a different kind of treasure, one particularly interesting for me. A nice fossilized cobble with fossil clamshells. And this was very much a surprise. You can see that the light colored rock, it's a sandstone, a fine to medium grain sandstone, and it contrasts pretty markedly with the volcanic rocks that you typically find on the beach. So I took some pictures. I brought this back to Vancouver, took some pictures of the fossil, and you can see it here. This is a Canadian loonie coin, $1 coin for scale. And this is the fossil, the cobble in different orientations. And you can see here that it's composed of many, many fragments or individual whole valves of clamshells, and but just packed in there, very, very dense. You can see clamshells pretty much throughout the whole cobble, mostly fragments, but the occasional full shell preserved. And if you look at it from one side, this particular side, you can see that a number of these shells are oriented convex up, well, at least parallel to each other with convex side like this. And this suggests to us, now there's one here that's concave, but a number of these here, here, and there was another one somewhere, are all convex up. And so this suggests that this was probably the sea bottom, and these shells accumulated on the sea bottom in a lag. If the shells are convex up, the currents that are on the sea bottom typically will disrupt them and flip them over. Not every one of them, of course, but this probably indicates to us that in general, we can assume that this direction to the top of the image was the original up direction of these beds. Not a critical point, but I do want to emphasize the fact that these cobbles are just packed in here. I'm sorry, these clamshells are just packed in here, very densely associated. So if we look in detail at these forms, these fossil forms, we can pick out a couple of different morphologies present. There are some shell fragments which appear to be flattened, relatively flattened, and characteristically covered with very fine ribs. They're not particularly well displayed in this particular view, but they are in there, trust me. And then the second form we also see are more rounded shells with a higher umbo, and they have more coarse ribs. And you can see the coarse ribs, particularly in this mold here. So two different principal forms of bivalve. Now we know from studying these fossils, at least, I do, that we can assign these to the genus Buccia, after von Buch, who was a Russian paleontologist. And Buccia has been around a long time. Buccia is very commonly known in the boreal regions or the high latitudes of the during late Jurassic and early Cretaceous time. And again, in this particular cobble, the Buccia shells are all very densely packed. They're oriented in multiple different positions, and the appearance here suggests that this was deposited in a high energy environment, probably at the shore face or just below it, subject to a lot of wave action. So the interesting interpretations that we can conclude from just looking at the cobble itself. Now, to get an age, to understand the age of these fossils, you have to go to the literature, and this is a publication of the Geological Survey of Canada by George Gillespie in 1965, I think it is. And Gillespie described the Buccia species from Western Canada and the Arctic in a series of publications, very extensively packed full of fossils, just like the accumulations in our cobble. Gillespie's plates are sometimes challenging to interpret because he did pack in images to every single space he could find. But the important thing here is that we can see several forms which mimic very closely what we've got in the cobble from Mukilteo Beach. There's a fine-ribbed, relatively low beaked bivalve called Buccia kaiserlingi. And then there's also a more coarsely ribbed form, as we see down here, which has a higher umbo. And this is identified as Buccia pacifica. And these co-occur in rocks on the Pacific coast of Canada. So we're very, it's very close match to what we have in our cobble. So that's really cool. And now, together, these two fossils indicate a mid-Valanginian age of about 135 million years ago. So what does this mean? This is a little bit of geology lesson for those who don't follow geology in particular detail. And this is the geological time scale. The oldest part of geological time is shown on the right bottom, and the youngest parts of geological time are shown on the left top. This is not to scale. This is about 4 billion years right here, 3.5 billion years, and this is only about 145 million years on the left. But this part of the column here is what we typically encounter in looking at rocks from British Columbia and Pacific Northwest, right? The Paleozoic, Mesozoic, and Cenozoic. And so this is kind of a starting point. And if we look here for mid-Valanginian, I told you the age was, it's down here and where the yellow arrow is, and that is an age of about 135 million years, give or take. So what are these stages? What are these complicated names? Valanginian, Campanian, Santonian. Coniacian is my favorite. These names come from regions of the world where rocks with particular fossil assemblages are very well displayed. For instance, the Campanian stage comes from the area of Champagne, France, which everybody knows is well known for more important things than its fossils, in particular champagne. And again, my favorite is the Coniacian, which is also from Cognac, France, and home of cognac, very sophisticated wine. So each of these stages are characterized by their own unique fossil assemblages, and we use this information or these assemblages to successfully date successions of rock in around the world, essentially. And wherever we have fossils that we know are of Valanginian age, we can then say, well, we can correlate these rocks with the Valanginian stage in Europe or wherever that type section happens to be. Now, a little bit of a complication that we have in the Pacific region is that correlation to the European type sections is challenging because we don't necessarily have the same fossils over here. And if you look at a map of the Cretaceous world, the upper map shows the early Cretaceous, the lower map shows the late Cretaceous. You can see here that the Atlantic in early Cretaceous time was very incipient, hadn't been fully developed yet as a through migration route. That took until the late Cretaceous when seafloor spreading moved the continental masses of Africa and South America and Europe and North America far enough apart. But what these maps are interesting in showing is that, first of all, they're very land-based centric. And so, these beautiful maps by Ron Blakey give us a wonderful view of what the world looked like topographically, but they're not really to scale. And the Pacific is vastly undershown here by scale, relative to its size at that time. The Pacific was much bigger than it's shown here because this part of the world was smaller than it is today, right? So if we look at the Pacific region, even this map is expanded and doesn't really show the Pacific in true scale, but you can get a sense here that the current systems in the Pacific region were pretty much independent of those in Europe. And to get from the Pacific into the Europe region, fossils would have to go through the Arctic. And so it means that most of the fossils that evolved in the Pacific region really didn't get into Northwest Europe and vice versa. So that's a little bit of background about our Valanginian time period and the period of time in which our fossils lived. So how old was that cobble? 135 million years, right? But it's very interesting. We know it's a cobble. It's sitting on the beach. Where did it come from? And if you look at geological maps of Washington State, you'll find that rocks of this age are exposed in two areas. And Mukilteo Beach is down here. The two areas are first on a small locality in the San Juan Islands. These are the San Juan Islands here. And Speeden Island is a small island here, pretty bare, rock and grass, and bird sanctuary. And there are fossils there that contain, or rocks there that contain Buccia fossils. Now, unfortunately, the Buccia fossils that are there on Speeden Island are younger by a couple of million years than the mid-Valanginian forms we have. So they're different fossils, different fossil species. So we can rule out Speeden Island as a source for this cobble. So the other opportunity is in the Mount Baker region of Washington State, very close to the 49th parallel. This is the 49th parallel running through here. You can see that, there's a transition at that border between the USA and Canada. And but in the Mount Baker area, again, the Buccia fossils found there are a slightly younger. They're comparable in age to the Speeden Island succession, and they're also found individually in mudstone. So quite different appearance there, as opposed to the Mukilteo beach cobble, which is hundreds of specimens all packed into an accumulation. So it doesn't seem the Mount Baker area is a likely source of these cobbles as well. So where do we have to find them? And an opportunity exists up in the Harrison Lake area. If we look at the geology of the Harrison Lake, it's kind of interesting. There's a nice Mesozoic package of rocks preserved there, Triassic, Jurassic, and Cretaceous. And this geology was worked out by a fellow named Colin Crickmay in the 1920s, and then in more detail by Andrew Arthur, who was a student at University of British Columbia, who worked on these rocks in the late 80s and early 90s. And so Andrew developed this very detailed stratigraphic succession for Harrison Lake area. And in this particular interval of the early Cretaceous, he recognized what's called the Peninsula Formation of Valanginian age. And the Peninsula Formation consists of sandstone and conglomerate with, very characteristically, shell beds. Now, this particular photo here is from Arthur's publication, and it's not that great, but you can see hundreds of these Buccia shells just sitting on the surface of this particular exposure. Thanks to my colleague Jim Munger at the GSC, I got a better picture of this area. It almost looks like the same rocks, but it's not. But it is the same locality, and you can see here the clamshells much better displayed, and the different forms, relatively fine ribbed forms, and anyways, you'll have to take my word for it, but these are Buccia kaiserlingi and Buccia pacifica that comprise these shell beds in the Peninsula Formation. So a very close match for what we have in our Mukilteo cobble. So that's pretty far away from Mukilteo. How did these fossils get down there? And the answer lies in Pleistocene glaciation. So during the Pleistocene, 10 to 25,000 years ago, approximately, ice covered vast areas of Canada, virtually all of Canada, not all of it. There were some corridors that remained ice-free, but for short periods of time, and moved southward down into northern United States as well. So this map here shows the extent of the Cordilleran ice sheet in southwestern Canada, and this map here shows the this area right in here. Okay, and you can see here that in British Columbia, the ice pushed south in two different areas: the Okanagan lobe here in west central Washington State, and then the Puget Sound lobe here in the Puget Sound area of Washington State. And this map on the left shows kind of generalized interpretations of the flow directions of the ice as it pushed to the south. Now, of course, the ice is was very, very thick in the central parts of the ice sheet, thousands of meters, and got progressively thinner as you got close to the edges of the ice sheet. But the ice is always in movement, and its direction of movement is controlled by the underlying topography and geology. So here we have a detailed map showing the Puget lobe and the locations of our important spots here: Everett, which is right around the corner from Mukilteo Beach, right here; Victoria, Vancouver's off the map to the north, as is Harrison Lake area, but you can see Mount Baker here, and Speeden Island would be this one right here. So this map on the right here shows you the thickness of the ice, and you can see that from a great thickness of 2,000 meters in south central British Columbia, it's thinning as you get to the margin of the lobe down to 300 meters here. So Mukilteo looks like it was under about 600 meters of ice during the maximum extent of the glaciation. So I really like this map. It's freely downloadable from Washington State Geology. I'm not a glacial geologist, but I think this is a really neat map because you can see here that there are many landforms that are found in Washington State and Puget Sound area that are based on or derived from the movement of the glaciers across the landscape. And you can see here these particularly elongate features, which are essentially recording the movement of the ice, the directions of travel of the ice as it advanced across the Puget Sound area. Just a really nice looking map. And so how does this work? I mean, you have the ice pushing across the landscape, and what happens is at the base of the glacier, the ice moves along and it grinds up, picks up, erodes rock off the bedrock. and picks it up and entrains it in the ice and carries it along. What unfortunately for fossils, if this happens, typically these rocks get ground up by the force of the ice, and they form like a glacial, fine glacial sediment at the base of the ice, which is characteristically clay-sized and silt-sized, and will often form the bright milky blue color that you see in glacial lakes today in the alpine regions. And that's due to the suspension of these really fine particles of rocks in these lakes that were originally derived from grinding up the basement underneath the glacier. So if our cobble had been picked up by one of these glaciers going over it, it probably would have been pulverized, right? So why didn't this happen? How can we have a nice cobble, a large cobble with all these fossils preserved in it? And the answer, I would suggest, is that the cobble was carried in a medial moraine down through the ice field. And medial moraines, well, when a glacier is traveling down through a mountain valley, you have the ice traveling down the center of the valley, and to the sides, debris rolls down off the mountains and accumulates in deposits we call lateral moraines, lateral to the side, at the sides of the glaciers. And when two glaciers converge, join together, their lateral moraines converge, and that becomes a medial moraine because that moraine is now within the body of the ice as opposed to at the side. So I would suggest that this cobble probably fell off of a hill here adjacent to the ice in southwestern BC, and then ended it in a lateral moraine. As the ice moved south towards Puget Sound, it coalesced with other glaciers, and the cobble then traveled in a medial moraine down to the Mukilteo area, where once the ice melted and receded, the cobble was left on the shoreline. So it's a plausible story, isn't it? A cobble of ancient Bukia clams hitchhikes from southern British Columbia to Washington State, and they only had to quarantine for 135 million years. Well, that's it. I want to thank Mukilteo Historical Society for encouraging this contribution, and as well John Clegg and Jim Munger from Simon Fraser University and Geological Survey of Canada, respectively, for graphics that they provided to me to use in the talk. I'm happy to answer any questions, so fire away.
Thank you, Jim. A wonderful presentation.